Hello everyone, welcome to CSC webinar series of IIT Jodhpur. So today we have Professor Kalyanmoy Deb with us from Michigan State University. He'll be speaking about explainable AI using non-linear decision trees. Thank you, Professor Deb, for kindly accepting our invitation and joining us. Over to you now.
Thank you. Good evening, everyone. And thank you, Pallavi, for arranging this. We've been talking for quite some time to find a suitable time, but we just ended our semester. So yesterday I submitted my grade. So this is the perfect time to do this talk. So yeah, I work in different areas related to optimization of different kinds, and then artificial intelligence and machine learning. Most industries around here are moving into use of some kind of machine learning methods and AI. So it's a big thrust over here. And I find that optimization methods are core in any of the machine learning and AI methods. So I have a unique position in order to take some of my optimization research and apply it to problems which requires machine learning, or even improve the machine learning algorithm. So there is one such application I'm going to show you. This was an industry-funded project to explain how artificial intelligence works. So I'm going to mention to you what kind of artificial intelligence we'll be talking about, but in short, they are known today as XAI, Explainable AI. So I am Koenig Endowed Chair Professor here at the Department of Electrical and Computer Engineering at Michigan State University. I have created a little lab here called Computational Optimization and Innovation Laboratory, in short, COIN. I moved here about 10 years ago. And before that, I was in IIT Kanpur for 20 years, and I had a lab there called Kanpur Genetic Algorithms Laboratory. And I worked for 20 years before coming here. So here's my email address and my CoinLab address and my personal web address. So this is my CoinLab symbol, and this is the Spartan symbol for Michigan State University. All right, so what I plan to do is talk about that AI and optimization. Of course, I don't have to tell you that they've made a big impact or major thrust in computing field. But I'm going to be mainly talking about this explainable AI, but I just wanted to connect that with some of the other activities that we often do with knowledge. So either we come up with systems that are knowledge driven, because knowledge is already available in some sort in solving almost any practical problems. Now, there is a bit of dichotomy that I would like to point right in the beginning. When you are doing academic research, and if you're using some kind of knowledge to change or update your algorithm or your methodology, sometimes in academic journals, these are considered not so pure work because you have used some knowledge. But if you try to go and use any industry problem, in fact, if you don't use some of their knowledge, it's a bit insulting to them, saying you don't need their help, that they have so many years of experience, and you can just bypass them and then solve a problem. It's better to utilize what knowledge they have in what form, and then update your algorithm with that. So there is a big gap between practical research or applied research versus more academic or theoretical research, which I'm facing when you're trying to submit papers to journals. But there are knowledge-driven systems, there are knowledge-based systems, and there are journals and all that. So some of those you have to take, but you could do a lot of formalism also using the knowledge that the user have. So it depends on your interest, and you can actually consider using knowledge to update your algorithm. So knowledge-driven systems are those where you already have some knowledge and you are trying to update your solution procedure. So that's obviously very clear, and we should use if knowledge is available. The second is, you may not have any knowledge available from before, but after you solve the system with whatever methodology you have, like you've been working on, for example, some autonomous vehicle design problems, lane merging and stuff like that, using some kind of Nash equilibrium concepts, So these are theoretical concepts, but once we get these results, we then see there is a lot of knowledge that are stored into these systems that we have optimized. Now we can acquire knowledge from the systems that are solved using some standard method. Okay? And so you can discover knowledge from it. So once you discover it, then they can stay as rules, or they can be the next time if you're applying them, then you can use it. So both ways you can use that. But what I'm going to be talking about today is extracting essence. So there are certain AI methods, for example, reinforcement learning or deep neural nets. They have been used for quite some time now, and they are very successfully applied in solving various control systems, games, and other problems, computer vision problems as well. But after these are solved, you want to now understand how it is solving it. So far people have been trying to solve these problems, and they didn't bother much about how they are solving the problem. But once this field has matured a bit, the next question is coming is, can you explain how your DNN is classifying these different objects, different images, for example, or some manufacturing system, how is it able to decide that this manufacturing system is going in the right way and that one is not? So if you can discover that very early on, then you can terminate a process that's not going well or modify the system as it's going. So understanding of how a system is working, particularly an artificial system, is very, very important. And people are now paying attention to this, that can we interpret how these systems are doing? So there are various ways of doing that. I'm going to be talking about one particular approach which we developed here, or in the process of developing, I should say. It's called nonlinear decision tree approach. So decision tree approach, probably most of you are aware of, but I'm going to extend this to a nonlinear version of it. I'm going to explain that, how I'm doing it. And then I'll show you some results on some simple problems before I conclude. So just one slide on those two aspects I mentioned, a bit more. So knowledge-driven systems are systems for which, please stop me at any point if you have a question or if you want some clarification or some comments. So I have a system to be solved or simulated, but I already have some knowledge to me. So I can then utilize that knowledge in developing the algorithm. As I said, obviously this might require some problem-related data, environmental data, and stuff like that. And then I come up with a methodology that is knowledge-driven, and I get a solution at the end. Or I haven't used any knowledge because I didn't have one or I didn't want to use. But then after I solve many of these systems, many of these problems with the system that I developed, then I analyze those solutions and come up with knowledge. And that knowledge can come back next time I'm solving it and solve this system. So these are the two approaches, knowledge-driven and knowledge discovery of systems. But when you're trying to do any of these, that you want to incorporate knowledge or you can extract knowledge from the data, there is an optimization task that you will have inside. So let me spend a few slides on different approaches for optimization that can be useful for this. So optimization methods are useful in many, many different problems. As you see here, I try to put it in one slide. Whether it's a modeling problem, this is a blast furnace for steel making. It's a very complicated process, having a lot of inputs, and there is a many hour long process that goes on inside the blast furnace and some other sub processes before you get the steel. So you can think of this as a steel quality of some kind, like properties, as a function of all the inputs that you are putting in. So can we model that if I change anything here, how is the steel quality is going to change? So that's the modeling part. Oftentimes, science can take you only up to a certain point. You need to look at a lot of data that the steel companies are producing and analyze them and come up with a model from data as well as some partial scientific informations that you may have. So many engineering systems have such complications, and you need a good optimization method which will then figure out what would be the model. Then scientific experiments can be expensive to do. If you've done 10 experiments, you are planning to do the next 2 experiments, you have to judiciously put your design of experiments so that maximum information can come from those 2 experiments. So there are many ways to optimize and come up with what you have done and what are the next steps. Then, of course, design and manufacturing takes the lion's share of optimization task in practice. You see lots of parameters, the angle, the thickness, the material, curvature, and many other things that comes in a design. You need to know how to set those parameters so that one or more criteria is satisfied. These days, multi-criteria optimization has become also a commonplace in industry. And then you have placement problems. These are combinatorial problem. In a printed circuit board, for example, you know how the connectivity of every component should be theoretically, but now how do you place it so that you have the minimum area? Or you have a good, from the heat transfer point of view, there is no hot spots in the circuit. Another version of that is the supply chain. Again, it's a scheduling kind of problem that many entities are involved. Then you have optimal control. These are a little difficult than some of these optimization problems because now your variables are not just a few numbers, but here there are some profile, right? Like for example, how shall I set my temperature inside a furnace so that I require minimum energy to heat up some looms, for example, or controlling some power systems. So these are time varying usually, or some distance varying parameters. So it's some kind of a profile that you need to find out to optimize certain things over a period of time. And then the extensions of some of these can be in stock market prediction, weather prediction, and where you have a combination of the modeling part of it that you take from the past data and then predict how is that going to end up in the future. Then you have data mining. There's a lot of work coming there in clustering and then classification, and there are a lot of issues here that comes in. The data comes from different sources. Data from source A and data from source B, how are they related? Are they the same cluster, or they're different, and so on and so forth. And when the data is huge, this is not an easy task to do. So there are a lot of machine learning methods, which again, internally have to be optimized, because at the end of the data mining or the machine learning procedure, you actually formulate an optimization problem like lasso or other methods. Then you have intelligent system design, any kind of intelligent system, whether it's autonomous vehicles or whether it's something else, and an optimal intelligent controller inside a car or anything that you're doing of that sort. There is a connotation of intelligence with optimization, because if you think or set up your optimization objectives and constraints properly, you can bring in the related intelligence that you need in your systems to have. So it's a matter of choosing the objective functions properly, so that if you optimize it, you get some solutions from the search space that are special and may have some intelligence that you wouldn't have if you just taken any arbitrary solution from the search space. So different problems, as we see in practice, all can be solved using some optimization method. So while it is so much prevalent in various kinds of practical problem solving, when I give this kind of talk to various universities, one question they ask me is, why aren't we then making such a topic as a compulsory course for our undergraduate education, at least undergraduate students graduating, and because many are not coming back for graduate studies, so that's all the degree they have. Some knowledge about optimization is useful for them because you see the breadth of problems and they can solve. Some universities have adopted it, but many universities haven't, because the one simple reason is that there is no single algorithm that you can have to solve all these problems. So you need to have some kind of research to come up with an appropriate algorithm, optimization algorithm for every problem. So it gets a little complicated, but at least some introduction to a part of some course, or maybe a full course for undergraduates, is a good idea to have at some point. And I can discuss more about it later. Now let's talk about optimization algorithms then, because as I said, there cannot have one algorithm most appropriate to solve all these problems. But there are all these algorithms that are out there can be divided into two classes, point-based and population-based. So point-based method starts with a point. If you're trying to maximize, for example, a function, objective function like this, this point-based method starts with one guess point or whatever is a currently known solution, and then it modifies it in a point-by-point method in the hope of optimizing the objective function that you have. So if you start from somewhere here, you may get into some of these peaks. If you start from somewhere here, maybe you can get to the global peak. So these kinds of methods, because they're point-based, you could do a lot of math. Usually for convex problems, there are provable algorithms that will guarantee no matter where you start, it's going to take you to the optima, because in most convex problems, there is one optima. But in some convex problems, there can be multiple optima with equal value. But if you go to a nonlinear problem like this, which is clearly not convex, then those methods do not work. But if your problem suits into the premises of those algorithms, that assumptions that the algorithm needs to have a proof, then there is no other better algorithm. You should always stick to these point-based methods. So they are usually mathematical and math-oriented, and they work pretty well in giving you a local optima. But if the assumptions are violated, there is no guarantee that it's going to give you any optimal solution, whether local or global. But on the other hand, the population-based algorithms are quite different. They are usually motivated by some heuristics, some kind of physical principles or some other principles that we see that has a connotation to the optimum. So here we can start with a number of solutions, for example, and then in next iteration, I can get into an overlapping population, but some of the solutions are better and some solutions from the past can come. And like that, in the population-wise, the algorithm moves. Because there is a number of points that you have, at some point you can reach the local minima or maxima, but then there is a population. So maybe some solutions are going over there, which is better than a solution here, which is at a local optima. Then the whole focus is going to move there. And then eventually you can go, has a better chance of getting to the global solution than with these kinds of methods. So if you're thinking of a more flexible and global optimization, a population-based search becomes quite interesting, because we see around us, nature has figured out lots of near optimal, or in some sense optimal solutions, like hexagonal shape of a beehive can be proven to be the optimum of any regular shape. In fact, this is one common question I give to my students in my optimization class, that they have to prove that hexagonal design has the maximum stiffness for an unit mass of any other topology that you may have. Similarly, you can see the shape of a whale, or the birds fly in a way that can be proven to be optimum from fluid mechanics point of view. So there are some reasons for us to look at nature, because nature has taken a lot of time to perfect this, but we need to speed up that process when you are following these ideas. So we just consider some macro concepts from these natural principles. So if you look at this evolutionary optimization, as it's called these days, but it started with this genetic algorithm concept way back in before even 1975, I think around 1962 when the first idea was proposed. But around early 70s, they have coined this word called genetic algorithm, because they were kind of mimicking the natural genetics and natural selection process. These days, we got out of the genetic term. We call it evolutionary optimization, because there have been questions about how genetic is our genetic algorithm, and that's a good question to ask. But because we follow natural evolution in this process, we call them evolutionary optimization. So the way this works is you start with a solution, with a good way to represent your solution. They could be your real parameters, or you can represent them in binary strings, or you can represent them in any other way with some random keys, various ways you could do that. Start your algorithm with the iteration counter, we call them generation, to be 0. Initialize a set of points. So you start with a number of points, call it population, and then evaluate them. And then if you're not terminating, then change this population to a new population by doing first selecting good solutions from P, and then taking this good population, which is called the mating pool, P dash, and apply some algorithms to the P dash in order to get a new population we call offspring population, evaluate these new solutions, and then combine the original parent population with this offspring population and choose 50% of it, that maybe the top 50% of it, increment the counter and go into the loop till you terminate. So for a simple example, if you're trying to design a can with 2 variables, diameter and height, I can think of any way of coming up with my diameters and height. Here I have used a representation, which could be a binary representation, 5 bits for diameter, 5 bits for height. And if this, so this one will be decoded to 8 because this is the most significant bit, and this is the next one. For a 5-bit, this will have 8, and this will be 8 plus 2, 10. So this string represents a diameter of 8 and centimeter, let's say in unit, and height of 10. So now I can go and evaluate how much it's going to cost me, and I'm putting the cost over here. So that's my representation. I can initialize some cans like this by randomly creating chromosomes, getting the diameter and height, and calculating whether it's feasible or not. There could be a constraint that says, I want some volume inside. So these two solutions are not satisfying the volume, so they are infeasible, but these 4 solutions have the requisite volume, so they're not infeasible, they're feasible. So because they're infeasible, I'm adding some penalty saying how much off we are from being the requisite volume. So this one is 30 cc away, this one is 40 cc away, so we add this penalty to increase the cost. So it's actually cost me, let's say 9 rupees, but I add 40 more rupees, so its total cost is 49. But these ones are feasible, so I don't add anything. So that's my evaluation process, initialization and evaluation process. And then first thing I do is select. So these are batch solution. You see in my selection process, I did not choose them. And in the process, the best one in the population got 2 copies, 23, 23. Second best also got 2 copies. And the mediocre ones got 1 copy each. So there is a procedure called tournament selection, or there are many selection operators that you can use. These are probabilistic operators by which we do this process. After the P dash, the mating pool is created, we take 2 individuals from it, like 23 maybe and 37, and we look at their chromosomes and then do a crossover. It's basically the mimicking the biological crossover, which actually happens in multiple places. So you could do a multi-point crossover as well, but here I'm showing you a single point crossover where the right side gets swapped here, and you get 2 new solutions because your chromosomes are now different. You may improve from before, you may not, but that's the process you follow. And then you have to do some mutation, take one of these solutions, change one of the bits, just flip it to its complement. And again, it may improve it, it may not, but you keep doing that. So once you do it, you get a new population created like P-double-S-T, compare with the original P and keep the survivor. So that's how you go. This is a very vanilla generic algorithm. This kind of method will not work when you're solving a complex problems, but you can use the concept of selection, picking good solutions from the population, recombining 2 or more solutions to create new solutions. That concept, this procedure can change, but you can use this concept, and you can use problem information right here. And then mutation is a local change that you're making. So this is more like a local operator. This is more like a global operator where you're taking 2 or more solutions from the population and combining them to get a new. This is an operation that is not there in any other optimization methods, and this operator make them unique for evolutionary methods. But so this kind of ideas work pretty well in different problems. Here is a very simple problem with 2 variables I'm showing, where my optimum is here, but you see it starts with 10 different points in the entire space, and pretty quickly it recognizes this is the feasible region. So it comes here. From here on, you can actually leave the GA or these evolutionary methods, because you see the population concept is gone. So it kind of creeps near to the optima. But finding these global basin of where the interesting points are using such a concept is a very good idea. So I think best is to hybridize with the population-based algorithm, start with the optimization with that, and finish up with a point-based algorithm. And we've been developing lots of such hybrid methods for solving practical problems. Now I'm getting into more practice-oriented and applied concepts. If I am interested in designing tall buildings, and I have, let's say, many years of experience in doing that, if I see around me different buildings, I see that one properties I notice in them that as you go higher and higher up, the cross-section of the building reduces. And there is a very good reason. If you're a structural engineer, you know that it's more like a cantilever beam. All the wind loads that will be coming here will have the maximum moment, bending moment at the bottom over here, at the root of this. So as you go up, your bending moment reduces. So which means you don't need to have a much more area as you go up. In fact, if you reduce, then you get optimal design. So why don't we use such a concept in our recombination and mutation or even initialization process. So we came up with a semi-independent variable concept called SIV. And when you apply to problems like that in mechanical engineering problems, without that, this is the overall, I think, what's the weight of the overall structure. It reduces to some value, but if you use this kind of semi-independent concept, then you could do much better weight, much quicker than you've done that. So this is what I mean is if somebody knowledge is available for many years of experience, why ignore it? Now the question is, how can I use it? What knowledge I should utilize? You then kind of focus your research towards that. There is no question now that we are not going to be using the knowledge. The question is, how do we extract knowledge and how do we modify our current algorithms to implement this knowledge? So the research focuses over there. I will be putting some of the related papers as I'm going ahead. For more information, you can see that. So there are, again, some problems from practice where you can have very large dimensions. So here is a problem I had while I was in Kanpur, working with some companies, and this is a PTC Industries, which actually is a foundry. It melts in some batches of some amount of metal, and then they have to decide which of these castings that they have to do. And this is a big company where they have many, many orders that they have to make from these castings. So it's more like a resource allocation problem. Later on, I found that this comes under a common problem that is kind of described in the OR. So the only problem with this is that this can be very large dimension. So the industry's problem, when I looked at, they needed about 50 to 100,000 variable problems. So for any optimization algorithm, anything more than few hundred is a huge problem, because most of these optimization algorithms have the curse of dimensionality. They start to kind of show their lethargy in getting to the optimum when your dimension increases, right? But this problem was already very high. But one good thing about this problem is that everything was linear. The objective functions, the constraints were all linear. The only difficulty was that every variable was an integer. So it's an integer programming problem. And most of the point-based methods use a fix-up called the branch and bound method, which actually branches the problem into various problems, and they keep solving each branch. When you have a large number of variables, the branching becomes so severe that you are not able to reduce all the branching and get to an optimal solution. So until about 1800 variable for this problem, I could use a standard software, which was IBM Simplex software that I used. But when I go to 2000 and more, it was not able to solve even after I ran for 15 hours with that algorithm. So what we ended up was developing a population-based algorithm to solve this problem. We said, we are not interested in the optimum as long as you give me 99.7% utilization. And remember, the optimum can be anywhere from here to 100% because you can't utilize more than what you've melted. So for all practical purposes, this is a very good number if you can find consistently solutions with 99.7% utilization of the metal. And for these problems, you can see the results. I could solve it in like 10 seconds, and this is about 50 seconds or something, 1000K. So less than a minute, I'm able to solve and give you a solution of 99.7%. So this was done, and then we had some restrictions of not able to publish for a while. After those restrictions go away, I got hold of some professional programmers because I needed to use every piece of the code properly. And then we extended this algorithm all the way to a billion variable version of the problem. Of course, that industry is never interested at this point, but just to show that the algorithm we developed can be applied to a similar problem, having 1 billion variable. There is no other optimization methods that I know at this point has tried such a large scale problem. So you're talking about a billion dimensional problem. It takes 6.2 days on our computer to get the optimized solution with 99.7% utilization. But this is a peanut, because if these kinds of problems in the industry is a 1 month problem. So if they have orders for 1 month today, I need less than a minute to come up with a plan or a schedule for the entire month. This I back calculated will be like about 1,500 years of orders. If they have today, I need 6.2 days to come up with a solution. So this is a small number compared to the duration of the problem. But these are impractical for now. But what I'm saying is the algorithms are scalable. As you can see, this is a log-log plot. I get almost a straight line performance. Every plot dot here having 99.7% utilization means that this is a polynomial time performance. This problem is an NP-hard problem, so you cannot find a polynomial time algorithm if you are interested in finding the actual optima. But these ones are, none of them is corresponding to the actual optima. There's a 99.7%, as I said, optima is in between this and 100%. So imagine now, if you want to go from any of these points and get to the optima, you will need an exponentially large type of computation. So just to get maybe at most 0.3% of more metal utilization. So for all engineering or practical purposes, these are okay if you can solve it in less than a minute. So that's the kind of concept, and we are departing from getting to the real optimum, but coming up with a near optimal or practical solutions and saving time. So my research has been always to come up with a practical algorithm so that they are real time, although we may be sacrificing a little bit on the actual optimum. And in many cases, these are fine. So we apply this on other problems. Here is another one where we take the knowledge of the forest managers and came up with a forest management problem for multiple objectives, biodiversity, because there are different kinds of species. You don't want to cut out all the plants of a particular species. You need to maintain biodiversity of what you are cutting. Similarly, simultaneously, you have to keep a note on the carbon storage. You have to maximize, and profit, you have to maximize. So we are coming up with a time-dependent method of cutting the forest. You see, sometimes it's getting thinned down because there was a cutting take place. Now here there's a big cutting take place and it thins down, you see. And then again, it grows. So we came up with a strategy by which these three objectives are traded off in order to find a solution. So these are complex problems, but our algorithms are capable, and none of this we are guaranteeing to be optima, but something that is reasonably well that you can utilize for practice. Little bit about now knowledge discovery aspect of it. So I mentioned that when you do a multi-objective, here are a couple of ways you do. This is my NSGA2 algorithm, which has got really very huge citations. Now, I think I saw the other day, it crossed about 40,000 Google Scholar citation on one paper on IEEE transactions that we have on NSGA2. And you can see how it works. On 2 or 3 objectives, it comes down like that in a front and gives you the Pareto front here. So this is objective F1, objective F2, and you can get a nice distribution. Here is another one where you are doing more than 2 objectives. This is a 3 objective problem, and you can see now you get a Pareto surface, and starting with the random points, it'll start, you can see how nice a distribution you can get on the Pareto surface on a problem that is really well structured. So these points are now working in iteration and getting there. So with these algorithms being developed, you actually get a number of Pareto solutions, as is shown here for a gearbox design problem of something like this. There are 28 variables we had. One of them is the module. Few of them are the gear thicknesses, and few of them are number of gear teeth. So what we observed once we find these Pareto solutions, that out of 28, one of the variables is really changing in a significant manner from one end of the Pareto set to the other end. All the other variables are more or less constant, as you see. This one is changing a little bit, 2 to 2.5, but almost the same. It could have been from a small to a large value, but all the optimal solutions have got some almost the same value. But this one, you see, there's a big change. So you can study after you get these Pareto solutions. Each dot is a solution. You can study and figure out what's changing, what's not. There could be relationship that this gear thickness should be higher than this gear thickness. All these analysis procedure can be done using machine learning. And I gave it a name. I call this innovation process, because every time we do this, there's some innovative principles we come up with. So I call it innovation from optimization. So in short, innovation. I've done lots of problems. You're formalizing some of these things, but this is the starting point of this extracting essence idea that I've been talking about. So, but it's also a knowledge, right? That we discovered that the module which is one of the variables that's something to do with the gear profile, has to be in proportion to the square root of power that you want the gearbox to be operated on. So if you have more power, your gear module is going to be high, and the diameter of the module is directly proportional to the module. So if you want more power, this is the recipe that you should increase your module. That's how your gearbox will become bigger and bigger, not in any other way, not increasing the thickness or number of gear tooth or anything. So you can generate some kind of a recipe of how we should change our design for different operating conditions. Some of these, when I talk in my class, students get all kinds of ideas. So there is a couple of students in my undergraduate class for optimization. They took this and applied the concept to a tic-tac-toe game, which most of us know how to play. So what they did is they found out that this game has 72,657 different ways of playing it. And it's a finite number. And each of the games now, they play against a number of good players. Again, every time it plays multiple times, it counts how many times it's making a draw and how many times it's winning and how many times it's losing. If it's losing, a particular strategy losing, then they don't show it in this plot. But if it's not losing, that means it's a feasible solution. Then sometimes it's making a draw, sometimes it's making a win. So based on that, you put the point. So this point, for example, draws so many times and wins so many times, right? So the location of the point is put here based on how many draws and wins you have. Once you've gotten that, your goal is to minimize the number of draws and maximize the number of wins so that you can think of the Pareto strategies. Here are 8 different solutions that they came up with. And now each of them has a flowchart of how you should play the game. They look at this and find out what is common in them. So what kind of principles are common? They found that these are the 3 that are common to all of these 8, but either 1 or 2 of them are present in the others, but not all 3. So what are they? If the opponent is 1 short of winning, block it, like something like this. If the center is empty, occupy it. If the center is filled, occupy the corner and the edge center in this order. So these are the 3 rules you learn very easily once you play a few times. But this was an algorithm that first was not given this information. It played against some good players and different strategies were considered and found that when you find this optimal set of points, they have these 3 things in common. So this could stay as a strategy for also coming up with optimal ways of playing the game or a good way of playing the games by doing this innovation concept. But this I call also a knowledge discovery because you are discovering knowledge from data through multi-objective optimization. With this background on this knowledge-based system and knowledge discovery, let's now move into these AI-based systems. I don't have to impress to you that there are different kinds of problems today AI are used, from medical imaging all the way to vision kind of problems and classification to manufacturing process design. So this is something we did recently. It's a friction stir welding. You get these 2 metals together and there's an anvil that comes from the top and you vibrate it. So all you get is, in order to fuse the material there, in order to make a joint, all we got was pictures like this, where how these deviation here is taking place with time. And then you can see if we blow this up that there is some vibration that's taken place. How much energy we are putting in, all this information are given to us. Now, as we started the process, after some time, can we say, is it going to be a good design? Or even we see the whole process, instead of doing any other further testing, just by looking at these data, can we say it's a good joint or not? So that means we're thinking of classifiers here and predicting whether it's a good one or not. So this kind of problems where you start from some images or some graphs, there is no real parameters. First thing we did was we came up with some physical quantities from them. For example, what is the slope? How fast it is moving? Or how in the first 1/3 of the operation, how much energy we put in, the next 1/3, how much we put in. So we get all this information derived from this, we get some real parameters, and then we apply our machine learning methods on them to find out what kind of relationships of them that present in order for these manufacturing process to be okay or not okay. So these are again pass, no pass kind of rules we came up with. Recently, we are working with another company where we have to predict silicon mass through a vapor deposition process, but it's a 60-hour long process. In 15 minutes, time steps go up to about 260 to 300 time steps. Can we predict after, let's say, 10 hours of the process, how much mass is going to be deposited after 50 hours and additional 50 hours? If that's not acceptable to you at this point, maybe you should terminate and not put all the energy to put there. It's a funny story. When these industry people came to me, there was an additional person from the power company, the local power company, who came with them. And this guy told me that you must be wondering why I'm here. The reason the power guy was there is that this company is the highest power consumers in Michigan. And this power company is very worried that they are demanding so much power. Of course, they charge them very high, but they are worried that much of their power is going to them. So they force them to optimize and make sure that somebody looks at it and says they're doing it in an optimal way. So this is funny that that some other associated supply company was interested in their optimizing their processes. But yeah, so all these are data driven. Again, terabytes of data were given to us, and then we analyze this through LSTM process and finally come up with a very good prediction. We are able to do now, this picture was taken a few months ago. Now we have about 2% error in the final prediction of the mass. But object detection, for example, so you get some image like this and you have to identify cars and identify a bicyclist or a cycle or a building or a stoplight or some other things from an image. There's been a lot of work going on, and it could be a video as well. So object detection becomes another big part of AI. Controlling, for example, games or autonomous driving, communicating with each other, and then which car should change the lane or not. So all this becomes a very important and popular problems today. But behind all this, usually there is a deep neural net that's working, getting all the inputs. This is just a small network I'm showing just as a sketch, but there could be a lot of pooling and other thing that goes on, but I'll talk a little more about that later. But I just got this from internet that the DNN, the deep neural net popularity, so you see that around 2018 at the beginning, it is almost hitting now about 100% popularity in the context of the machine learning and AI. So about 5 years, 3-4 years ago even, it wasn't that much. So there's a huge surge of work now in many different fields of using even natural language processing to various practical problems. So this is a common way of solving these image classification problems, where you have images, maybe with colors, and multiple images that you have of a particular class. You take the whole thing and consider some kind of convolution layer. You take a part of it and then collapse it and get some aggregate information. And then you do pooling, which is reducing the size now. And then another convolution layer, another pooling. So this combination goes on, and eventually you have a feed-forward classification layer to tell you the probabilities of each of these classes. So it can be a huge set of neural net. And every neural net that you see of this kind, there is a connection between two neurons, and you need to find what will be your weights. So there are different ways of coming up with the weight, but architecture search of this neural net, that means how the connectivity would be, is another part. So there's architecture search, which is called neural architecture search, and the weight learning, which is the next level search, which is what is with the weight, are two things together you need to solve. So recently we proposed using a bi-objective concept, maximizing accuracy of classification and minimizing the number of parameters, or how big is the neural net that you have. So you try to be on this corner because that maximizes the accuracy and minimizes the parameter. And you can see some of the results that we come from the Facebook, like the ResNet, for example, and the AmoebaNet came from the Google. This is our results, and there are a couple of advantages. One is we are better off in terms of both accuracy and less number of parameters. Also, we can find multiple solutions because of the Pareto concept that we are using in this bi-objective method. So there are many other such neural architecture search applications we are doing here, including some neural architecture transfer kind of work. But we are getting into these GAN concepts where you look at adversarial ways of making your solution more robust. So here is one simple example. If you take a pig's image, which has been classified by a DNN, if you add this noise to it with multiplying it with 0.005, all its magnitudes, you get this image. But when you now give this image to the DNN, which has been learned over many, many images, now that same DNN, which will consider this as a pig, is now calling this as an airliner, because these two are as if like two wings of the aircraft. And if you look at visually, there is not much change, okay? But to an artificial system was very easy to fool. So there are many adversarial systems that are coming out now in trying to fool what a DNN or artificial system has been developed. So if you're a good system developer and you want to come up with secure and trustworthy systems, you need to do yourself such a study on this whole area of generative adversarial network system, or in short GAN, that's coming out now to do some of these things. So why we need to then make, as I've been telling, that we need to have our AI policies or AI systems to be more interpretable. The reason is this. I mean, you can give me a DNN and you say, oh, I actually optimized over 2 months and came up with this. All I have to do is do this kind of process to see how effective or secure your system is. But instead, if you tell me how your system is working, for example, first my system is trying to identify the edges or maybe the eyes, and that's how it's working. And if you're able to explain how your DNN is working, then I would trust it a bit more, because it follows my logic, my human logic of how one should look at an image, right? But unfortunately, many work in this field is not doing that. And just yesterday, I was talking to somebody from an auto industry here, and he's a bit theoretical, but this is his complaint, that I don't want to get into these neural net models because they cannot be interpretable. And to very theory-oriented minds, that's not something that they want to go ahead. So a clear understanding of the working principle is needed if they want to be popular. Ability to respond unforeseen situations. So once you understand, you know that in some situations, my system is not applicable because I understand how it works. Or you can augment it in those situations by using some other augmentation to the DNN system that you may have. You will be able to extend to other similar systems. And clearly, you'll be able to identify use cases where they will not work, so that you have a classifier before you apply this that's saying, is my data now is applicable to this kind of system that I developed? And as I mentioned, to develop any trustworthy and secure system, you need to do all these analysis and interpretable, or explain how this AI system is working. There are various ways the research is going in these directions. For real valued data, there are not much work. But from the images, there are various ways they're doing. They're trying to understand every layer or every cluster of layers, what is being done at the end, and that it probably discovered all these images, certain patterns, and then the next layer is doing some other pattern, and there's a hierarchy of things. So they are able to explain this way. Or you take a particular image and you say, if I only have a minimal amount from the image, can I still able to say this is a frog? Okay, so what is that? Do I need the eyes? Do I need the mouth? So this part image is enough for you to say with 85% probability that this is a frog. On the other hand, if you just give these little patches, it's only 0.00001 or something. So yeah, so there's other kind of work, but then how do you partition and all that? That's not telling how your algorithm is working. That's basically telling that what part of it, if I then do as a post-optimality analysis, then I can say how my system is working. But is it the same for another image of the frog or another class? That's a questionable thing. So there are, the work has started, but I think we're a long way to go. But there are other methods like TSNE, for example, that shows for the handwritten numbers how they can be separated, and it's telling that all these images that you have there in these two arbitrary spaces here, they are all together, and that's different from how to recognize the number 6, then how to recognize the number 3. So it says, okay, my system has come up with a way to recognize each number separately, except 9 and 4, they look very similar, and maybe 1 is similar to 2, then 1 is similar to 0. And then this can give some human mind, okay, there is something going on here of what it has found. But what we came up with, an idea called decision tree for real parameters in your control system. Now, decision tree, and as it traditionally known as a cart, in a complex problems, the decision tree can grow to be such a big tree that nothing can be interpreted from this. So we need to, and in these decision trees, every node has one of the features, one of the variables to be less than equal to something or greater than equal to something. It's very, very interpretable every node, but overall, this is not interpretable at all. So we are trying to change each of these nodes into a nonlinear rule. So we expect that our rule base is going to be not as complex, but every rule will have some controlled complexity. So that's the idea that we are trying to do. I will be a little fast now, but just to motivate this concept, if we take a game from AI game literature, this is one of the problem called mountain car. So the way it works is this, is you see here, you have, this car doesn't have enough force so that it can go up the mountain. So it has to take advantage of the gravity, but nothing is told to it. So it has to come up with a strategy to go up to these mountains. So I don't know how to do that. So if you look at this is a small problem because you have two state variables. One is the velocity, the other is the position with respect to some coordinate system here. So if you have x position, you have x velocity. So when I learn a DNN, basically I call it an oracle, and I'm looking at when I'm applying a force on the right, when I'm applying a force on the left, and when I'm not doing anything. So when I'm applying a force on the left, I'm putting this with the blue color point. When I'm applying it to the right, I'm putting it with a green color, and nothing means the orange color. So you see, for all the DNN output, this is what I get at the XV relationships. So when you are over here, you are mostly blue. You are applying a force to the left. So you are allowing it to go this way so that it gains energy. On the other hand, if you are over here, you are applying a force on the right, and very few cases you have. But these are fairly uniform, but here there's some, and here you see, when you are here, you are a little confused. So if we now try to understand this DNN output, here you can get a clear understanding. You can come up with a nice classifier, but here you'll be totally confused, and a lot of non-linearities here because this one was green, then slight change of these, you can have blue or then you can have orange. So then my idea was, can we make it, brush it up with some boundaries that says, okay, if you're below this boundary and above, and you know, this boundary, if you are, so this below this boundary, you are a blue, and above this boundary, but below this and above this is green, otherwise you are orange. So how do you find this boundary? And then is it a good classifier? So now you're thinking of some nonlinear boundaries, nonlinear rules with X and B that you need to come up with, maybe not be one, but multiple of them, and then use that as a classifier, as an alternative to the DNN. But how do you do this is you're getting the data from the DNN and then trying to do some data analysis here in order to come up with this kind of nonlinear rules. Is it possible? And in this particular case, this one does equally good as this in terms of, in fact, this one I showed you is with respect to this NLDT output. We call it nonlinear decision tree. I'm going to show you the tree for this, but that's the whole concept, that we want to generalize now and express our rule base with simple functions of these variables. So now instead of getting into the details, we have a nonlinear decision tree that comes up, and you can see your rule is not going to be, now this tree is not going to be very big. Each rule here is nonlinear. It has certain structure. There are some weights and there are some nonlinear functions as you has there. The variables are multiplied, taken to the power, and these powers are my optimization variables and the weights are my optimization variables. This could be a rule. So if this is less than equal to 0, then you move on the left, for example, and then otherwise you move on the right. So what is this rule? Including the functional form as well as the coefficients are what we are trying to come up with a very efficient nonlinear optimization method. So instead of going into the details of this bi-level optimization method, let me go and concentrate on some results, and then I can take some questions at the end. So yeah, this is just detailing about the whole procedure of how do we develop our algorithm in a bi-level way. Okay, so the overall process is from the physical system, you develop first your oracle. It could be DNA, it could be RL, or it could be any other machine learning method. So once you've done that, now I can create lots of data from it because I don't need that anymore. I can create a lot of data and I know each class of data over there. Now, first thing I do a open loop nonlinear decision tree. We call it NLDT OL. So we come up with this tree one by one. We come up with these rules through bi-level optimization. Once we've done that, this gives me a rough idea of the rule. Now what I do is I go back to this environment and consider an episode. So here, every time step is a data point, but here, one whole process from start to end is my episode. And then I prune this network with changing my weights and changing also some of the rules here. And then I get the nonlinear decision tree star, or I call it NLDT star or closed loop training. And finally, this closed loop trained NLDT can be a competitor to this, or it is basically telling me how this DNN is working because everything started from the DNN. So this could be able to explain now with simple rules how this DNN is working. So that's the whole concept over it. It involves two optimization steps. Let me not again spend time here of how we are doing all this, but let's take the cart pole balancing problem, for example, where there are four state variables in one action, whether to push it here or push it that way. So we apply this concept and NLDT comes up with rules that has 4 to 5 number of occurrences of variables in the total rule base. On the other hand, the DNN, when we developed first, it had 4,480 parameters. So that many connection weights that we had. So it's a huge and non-interpretable system. But here we just have 4 variables defining our rules. How the rules is like this. So there is an absolute value with these. There are 4 variables. Remember x0 to x3. Only 3 of them are used. The x1 is never used in the rule. So if this is less than 0, you call it action 1. You have to apply action 1, which is applying a force on the left. And then if it's greater than 0, you apply it on the right. So it's a simple rule that actually mimics what the DNN is doing. And if I show you side by side, we can explain now what these rules mean by even analyzing it further and coming up with very simple concept that if this is lying between 2.39 and 5.06, this combination of these various variables, then you should go left, otherwise you should go right. And you can explain that. But you can see here how such a system with the DNN is able to balance, right? Very nicely. But look at how our NLDT is also balancing. You hardly can see that it's moving, but it's much more stable than this. But the reason for it to do this is we are actually able to come up with simple and kind of brushing kind of rules, because in the process of learning the DNN, there is no such regularity or other things that are considered from one time step to the other. But our NLDT concepts, those regularities are considered. So you don't have to be very, very complex. Okay, this mountain cart problem again, 2.97 variables versus 151,941 connection weights. So it's not understandable when I show you the whole neural net. But you can see the 2 rules that we come up with here to solve this problem. Again, here is the one that with the black box AI, as you can see, it does work. Yeah, and here is my NLDT that I already showed you before. It's also able to solve the problem. So the important thing here is if I go back, you do 100% of the time, we are able to move up to this flag. And this one, the NLDT OL, it sacrifices about 1%, 99% of the time. As I told you at the beginning, you get a good approximate solution to explain what your system is doing. So that's probably acceptable in all practical purposes. You're able to explain majority of the cases of how it's doing it. And now we make the problem a little more complex. This is a lunar lander where this vehicle has to land to a space, and there are about 8 different state variables giving 4 different actions, whether to start the main engine going down, left engine, right engine, or do nothing. And so this was a complicated problem, and we came up with about this NLDT4 with about 234 is the cumulative reward. And compared to the DNN, which does about 247. So ours is slightly less because higher is better. But you see in this problem, 94 plus minus 1.96% of the time it's successful, but ours is about 99% of the time. And you can see that the DNN requires 4,000, about 5,000 different parameters in it. And ours have very few, like 54 or so. Sorry, not 54. There are about 7 rules or something here. So if I show you the rules, there are 1, 2, 3, 4 rules in this case that's able to control these 4 different actions. And if I show you pictorially what's happening, this is the DNN on the left and NLDT on the right. When it comes around, and you can see both are doing equally well, actually. So this requires only 4 rules from start to finish. And this requires 5,000 parameters. And sometimes, and those 5,000 parameters, you're not able to explain how it's able to manage it. But here I have those rules with those 8 variables. We can analyze them and figure out how it's actually doing it. The last problem I'm going to show you is this Acrobat problem where you can add up lots of links. The goal is that there is a motor over here, so you can either put it on the clockwise force or an anti-clockwise force. The idea is to take this edge of this point going up and hit this point, so against gravity. So the question is now how you are going to control this, which way you're going to apply torque. This is a fixed torque that you apply here so that it goes there with the minimum time. So this problem can be scaled, and we've done on various versions of this problem, but I was going to show you just one result here. So this is how DNN does it. 0 means apply left torque, 2 means apply right torque, the torque in the anti-clockwise way, and 1 means do nothing. So you can see it's able to take it up, but you don't get a head and tail out of it, that if I do this, what is the next I should do? There is no pattern, but it's able to solve the problem. But here is the NLDT output, and you can see there is some periodicity that's happening, and you only do either left or right. You never do nothing, but that's a very systematic, easy way to understand how this torque needs to be applied, because this jerk is very important. You've been doing clockwise, clockwise, clockwise. Suddenly, you make a anti-clockwise. So that sudden change introduces a jerk and causes the whole system to get stabilized to where you are to something different. And then doing it occasionally is helpful. But you can see that with the DNN having, again, about 4,500 parameters, it's able to go up. And you can see that, but it's just that we don't understand how it's doing. Here is NLDT. And again, with just 2 parameters, and you can see that it's able to go up. So the 2 parameters are the angle of this bar and the angular velocity of that bar. Just those 2 determines what you should do. You can see the rule here. Just one rule. It's so simplified. If your xn is less than equal to this quantity, you apply an anti-clockwise torque. Otherwise, you apply a clockwise torque. So can you then take systems where you can understand the essence of what you should do? Your black box AI can solve it, but often it cannot explain. Can you then do this whole procedure that we talked about by creating data from the AI method and then analyze and come up with the essence? So I think I tried to talk to you about that we are, as a human, always curious that what works, what doesn't work, and try to understand the essential idea behind the system before we try to accept it. So optimization has been in the forefront in different computing fields, and they are needed for understanding these AI/ML methods. I talked to you about knowledge-driven systems a little bit and knowledge retrieval from systems. Both are important. Don't feel shy in applying knowledge in your system. But the third aspect that I talked about now is knowledge can be extracted from systems behavior, which could be a machine learning or a AI here. With all the 3 things doing together is probably the way to go. So we are really in the middle of doing all this. There are some initial results and there are some results which I cannot share with you, but this is an ongoing research at my lab. So with this, I'll stop. I know I've taken a bit of more time, but if you're still there and have some questions, I'll be happy to take. Thank you for your attention. Yeah.
Thank you so much for such a great talk. So we already have some questions in chat.
Okay, let me see if I can get to the chat here. So speaking here, this is not the one. Let me see if I can. I don't understand this system very well. I discarded. Let me see. This is a Microsoft Teams, right? Can you read me those, because I'm not able to
Yeah, sure.
get to the chat. Oh, those are the ones? I don't know. Let me see.
Ramon.
Okay.
Okay. So I can read, no problem. So this is the question by Ramon. When all of the solutions were not scalable beyond 2000 variables, this population-based algorithms was able to solve it for many more variables in minutes. So what was the trade-off in this process? So it's talking about a foundry example.
Yeah, okay. There we used a single objective, just of maximizing the metal utilization. So higher the better. The reason our algorithm worked so well is because it's a customized algorithm. We use the knowledge of the problem. What do I mean by that? So imagine you have a constraint, and I said that all the constraints and objectives are linear. So I have a constraint that says x1 plus x2 plus x3, let's say, equal to 1. Okay, so we had some constraints like that. They're equality constraints. Now, when I have that, I can use that constraint to eliminate one of the variables. So if I know x1 and x2 for my current solution, I pick x1 and x2. I replace x3 with 1 minus x1 minus x2. So that's how I repair my solutions to make sure my constraints get satisfied. So if it's linear, quadratic kind of constraints, very easily, and equality, very easily you can use them to repair your solutions. That way, you're doing two things. You're actually reducing your search space and also satisfying your constraints. It's a simple trick. And also the initialization can be done using some of these equality constraints. So we use this kind of tricks to, like we did in case of semi-independent variables. And then the algorithms behave completely differently. Is that method I can apply on another problem that will give me? Probably not, because you may not have that kind of constraints in your problem. But then I will look and see how I can best utilize your constraints, your problem description. And that's what I'm saying, that in many problems, the users can give you some such tips, some such ideas that that this constraint is more important than that constraint. Or I have seen that in order to get a good solution, if you increase this variable, you need to reduce the other variable because the overall weight has to be small. So if they know some such things, it's always good to use them. And that way you handle this well. But mixing of such a population-based idea with a point-based algorithm, like sometimes what we do is we have a population, we take the best solution from the population, and then go in approximating the problem with a, let's say, linear problem or a quadratic approximation. And then we solve that quadratic approximation problem, get a solution, and introduce it back to the population. So you can hybridize your evolutionary methods with known good solutions, but they are applied to the approximate version of the problem. So all this knowledge, unfortunately, you need for coming up with a customized algorithm, but this is the way to go, I think, for solving large-scale complex problems. Hopefully that answers what you're looking for.
So this is by Shikha Malik. So she's saying, thank you for the insightful talk. Are there any works related to drug discovery being studied in your lab? I think the concept of customized optimization would be beneficial in this field as well.
Yes, we haven't done anything on drug discovery yet. It's just a matter of, with whom are you working? But to me, yes, as you correctly noted, that at the core of these different problems, you have an optimization problem. And then once you understand, take it out of the context, look at the problem, and then you understand what kind of optimization problem is that. Is there all variables integer? It's a mixed nature, or there are some categorical variables, or there is a hierarchy, like there is an upper level problem, there's a lower level problem. Sometimes we have to do surrogate assisted optimization because the computing, evaluating one solutions can be time consuming. We just finished a project where one evaluation took 2 days on 500 computers put in a parallel way. So you can imagine, and they told us that you can use maximum 60 evaluations. So there is a budget of how much. So obviously they're not looking for the optimum with just 60 evaluations in 18-dimensional space. But all they're looking for is a methodology. Every time you work, it gives you something useful. It may not be the optimum, but something that they couldn't have found out manually by manually changing things. So that's all in many cases they're looking for. So problem comes from different context, but when you then look at the core of the problem, you can see some patterns. And what we are trying to do in our lab is trying to come up with methodologies for a broad class of problems so that now that an algorithm exists, you can see whether your problem falls into that category, and then you know that I can use that algorithm as a core. So it's mostly use case driven. I haven't got any drug company or anybody coming to me for a problem, but I think some related work we had done when I was in Kanpur in trying to do the docking problem, the protein docking problem. So that's one of my PhD students did that, but coming here, I didn't have the opportunity. But if you are interested and if you have data related to the problem, I would be happy to look at it and work with you. Okay.
So thank you. I don't see any other question in the chat. So if participants want to ask, then they may unmute themselves and ask. We can just wait for 2 minutes maybe.
Mm-hmm.
Yeah, I would like to ask you a question. I am Narayanan.
Mm-hmm.
This is basically, I am not from this background, but what it fascinated me is some of the things you have done with AI. Now with the things like quantum AI and quantum machine learning, how these things will will change the landscape of solving such a problem. Will that be advantageous to you, whatever you have done, or will it be kind of two different approaches?
I think the approach will stay the same if you are trying to understand how, for example, quantum AI system that you develop is working. So this is always the second stage, right? First stage is to have my system working, whether it's quantum AI, whether it's machine learning based AI, whatever I'm doing. First thing is to make it working. Once you made it working, then the next question is, do I understand how it's working in solving the problem? Because it's a network, it's totally data driven. A lot of people are trying to have some doubts about this system. You said, okay, they interpolate very well, but I know these systems don't extrapolate. So I need to understand what is your interpolation boundary, because if I want to reliably use it in my system, I don't want it to fail or somebody coming and fooling it with a simple change in my data. So I want to understand much better. So when you get into that stage, what I'm proposing here is you developed your system, have that, and create a lot of data with that. Now it becomes like a data mining problem, and then apply this NLDT and NLDT star on the data, and then come up with a logic of how your data that you've created can be explained using these simple rules that I'm saying. Now, not every problem can be explained. If this is a very complex systems and you at the core of it, you need every variable. Like I showed you in a 20 variable problem, 10 variable problem, I needed only 2 variables for this last Acrobat problem to explain. But I'm currently working on a lane change problem. There are 18 variables, and you need to look at all 18, because when we change lane, when you're driving on a highway, we look at all the cars behind us, in front of us, on the left lane, on the right lane, or on my lane, before I make a decision of making a lane change, right? So you cannot say, I only look at the car in front of me and the car in the left lane in front of me, and I move it, I merge it. I also have to see which car is behind me, which car is behind on my left lane. So certain cases, your rules are going to be complex because it's a complex way to make decision. But our method is flexible, that if you allow, you can control what would be the powers of this, and how many terms you're going to have, those all can be controlled. So if you're not getting satisfactory result, you can relax those parameters and you can get more complex and more complex nonlinear decision trees, but you don't have to go into these huge cart kind of design problems. So I think that principle, getting the data from your system, no matter what it is, and getting data and now try to analyze and come up with a reason how this data is working, is basically saying, I'm also telling you how your system is working. So that concept can stay. Okay. But I don't quite know much about the quantum AI idea, but maybe there are more you could do in that area by taking the piece of the quantum part and how it's helping to create the AI into your learning process here. But yeah, every problem is different, but I think the concept can stay.
Okay, thank you, sir.
So Professor Deb, we have one more question. Can we take one more question?
Yeah. My next meeting is 10, so it's okay. Yeah.
Okay, so this is by Jyoti Datta. Can all kinds of neural network problems be given an explainable form of approaching the same?
That's a good question. And the answer at this point is no, not with the way I'm doing it. For example, if you have images now, and let's say you want to do ImageNet or Cypher 100 or some of these image based that we have for computer vision purposes, and there are a lot of DNNs, our premises here is that we can convert your data into real numbers, right? And because it's all real number like x1, x2, x3, and I'm trying to find a relationship. We haven't gone to images yet. And then because there are already some propositions for images, I showed you one or two with the frog image and things like that. But our plan is to get an encoder decoder system from the images to get down to some real parameters from a decoder system. So we can represent an image with a bunch of variables. It could be an agglomeration of different parts of the image, and that we represent as a variable vector. And you need to learn that mapping, how to do it. And then we can apply this method on these real parameters and coming up with a set of rules. Now, how does it translate back to the image? Like, is it now saying some edges in the image or some color difference, or that will be a little difficult. But if you just care about explaining how your neural network is doing and not getting all the way back to the image, then I see some ways to apply this method there. But a simple answer to your question is no. If you have real parameters as your input, doesn't matter how many variables, but more like control systems. You have some state space and you have some state variables and some action variables. And there's an environment that dictates how, when you apply the action variable, how the new state space will be evaluated. Then those kinds of problems come this idea was developed for that. Again, as I said, much of my research is based on what problem we get from industry. So this is what I got from an auto industry, and that's what they're interested in. But then the questions are coming now, can we extend it to other kinds of problems like some of you are asking? So we'll be thinking more in that directions, but I think there's something here through understanding the process that can be generalized. But I don't want to make a sweeping argument now that it can be done to understand every neural net. Okay. Now, these are good questions. Yeah, so some of you may want to look at it together if you are interested, because I always like collaboration.
Yeah, it's a good opportunity. Yeah. So I think this answers the second question as well. Yeah. So there's no more question in the chat. So then probably we can wrap up here. So thank you so much, Professor Deb, for joining us and for such a great talk. It was so nice to have you. And thanks to all the participants. See you all next week. Bye-bye.
It's my pleasure. Thank you, everybody. Please stay
you.
safe. Yeah, thank you. Bye.
There's thank you messages now.
All right. Yeah.
Thank you.
Bye-bye.